All right, welcome. So we're looking at page 1 in the packet. We're just going to start out this motion chapter. So the first thing we're going to look at is how do we describe motion using words and graphs, and then we're going to move into equations. So the first thing we're going to start out with is some of these words. And so the way we describe different types of words that kind of describe the same thing is we use vectors and scalars. So that's what we're going to focus on with one specific example of displacement and distance. So let's get started. So vectors have two parts. Think about the V. It has two parts, magnitude and direction, whereas scalars only have a single part, S, scalar, single magnitude. Now when I say the word magnitude, anything can have a magnitude, a force, a distance, a time. A magnitude is just a number with units on it, so like 5 meters or 20 miles per hour. That's the magnitude. If we stick a direction on the end, we then have magnitude and direction. We have a vector. Unfortunately, due to copyright laws, I can't show you the little clip from Despicable Me, but if you were in class, you got to see that clip. All right, so down here at the bottom, we're going to focus in on displacement versus distance. Okay, displacement is our vector, and this cares about how far is it from the start to the end. It doesn't care what you did in between. Where did you start? Where did you end? And how far from that point to this point. And so it takes a straight line with a single direction between those two. Distance, on the other hand, cares about how far along the path you went. So let's look at an example on going to school. So you start at home, you end at school. Displacement just cares about where did you start and where did you end. And it has a very singular direction from home to school. Now, most of us didn't get in our cars, point our car towards school and just go. We probably took some sort of path. And so the distance would be that path taken. Whereas that displacement is that blue line there. Okay, so that is our displacement. And so you'll notice that our displacement has a single direction, but our distance, the direction is changing all the time, so it doesn't have a single direction. So we just talk about its magnitude by itself. All right. Now, a couple quick questions about relating distance and displacement. Could you have a situation where your distance, the path taken, was the same as your displacement? Yes, if you traveled in a straight line, you're right. Yeah, feel free. Feel free to communicate with me. Just yell at the screen. I know it's YouTube. It seems weird to yell at the screen, but go for it. Give it a try. Yes. So yes, this is true. Can the distance be greater than the displacement? Okay. Can the path taken be longer than the straight line between the 2 points? Most definitely. Yes. Thank you there. Yes. Good job. All right. How about, can the distance, the path taken, be shorter than the displacement? So can I draw a line that's shorter than the line that's a straight line between the 2 points? No. So distance cannot be shorter than displacement. When you ask it in the form of like, can I make a line that's shorter than a straight line between 2 points? The answer is no. It's a little easier to think about, but as you get more comfortable with these terms, those answers will come a little more easy. All right, let's take another example. Let's all remember the shuttle run from the Presidential Fitness Awards challenges we did in elementary school. In the shuttle run, you started, you ran out, you picked up a block, maybe an eraser, depending on the school budget, and then you ran back. And when you got to the start, you set the block down, not throw it, you set it down because we don't want to hurt others. You run back and grab another one and come back. And so in that time period, you ran out 5 meters, back out, and all the way back. So you ran that time 4 essential times, out twice and back twice, so 4 times. So what is your displacement? Where did you start and where did you end the shuttle run? Well, you started here and you ended here. So how far is it from the start to the end? Yeah, 0. But how far did you actually go? What was the path taken? Well, if we say it of about 5 meters out to those blocks, so you went 5, 5, 5, 5, so you went a total of 20 meters. So your distance was 20. So in this case, the distance was greater than the displacement. Yes, that was one of our possibilities. All right, let's take the 100-meter dash. Okay, so the 100-meter dash, you start at the start and you run in a straight line, preferably, yes, until you get to the end. And in this case, how far did you run? You ran 100 meters. What was your displacement? Well, how far is it from the start to the end? 100 meters. So they're the same. Now, they're the same, but I thought one had direction. Oh, I almost forgot. I got to put a direction on this. So maybe the direction of your 100-meter dash was west. You ran west. All right, so these are a couple examples. Now let's go ahead, and what we're going to do is we're going to use these definitions of what displacement and distance are, and we're going to get into more of a formulaic way of finding it. We're going to use numbers, plug it in an equation, etc. So let's go ahead and get that set up. All right, now that we get this set up, I got a few more questions for us. So we're going to now use an equation for displacement, which is delta x is our symbol for that. And delta, now a lot of us have remembered delta to be change in, but I want to be a little more specific. I want to call it final minus initial, and I need to be very specific about that, and you're going to see why when we do these questions here, where we try to find the displacement and the distance, and why is it important to do final minus initial. All right, so when we do this, delta x is equal to the final position minus the initial position, so we call this x sub 0. X naught is how we describe that. And the 0 here stands for at time equals 0. So that would be our initial quality. So let's imagine I have a little bug, and my little bug starts at the 0 centimeter spot and walks down my meter stick to the 40 centimeter spot. And again, this is going along with your packet, okay? So it goes along that 40 centimeter spot. Okay, so what is the distance traveled by my little bug? All right, so my little bug started at 0, it walked to 40, so it went a whole 40 centimeters. Okay, well, it went in a straight line, so I would expect distance and displacement to be the same, yeah? All right, so let's try our equation. So what is my final position? 40 minus my initial position, 0. So I had 40 centimeters minus 0 centimeters gives me 40 centimeters. Okay. Now, some of you might be thinking, well, what about direction, Mr. Foster? You said vectors have both magnitude and direction. All you have written there is a magnitude. And I want to show you where that direction comes in when we use our equation. So let's try another one. So now my bug starts at the 80 centimeter spot and walks itself to the 50 centimeter spot. So how far is it from 80 to 50? Well, that's 30 centimeters. But let's try our equation. Final position, 50 centimeters, minus the initial position, 80 centimeters. And if I do 50 minus 80, that gives me negative 30 centimeters. What is that negative sign telling me? That negative sign is telling me I am moving in the negative direction. So what we're doing now is instead of saying left or right or up or down, east or west, when we use equations, we're going to use positive and negative to describe our direction. So in reality, there is a plus sign here telling us that this is a positive 40 centimeter displacement. All right, one more here. We're going to start at the 10 centimeter mark. Our bug walks all the way over to 50, changes its mind, turns back and walks to the 30 centimeter mark. So what is the total distance traveled? Well, they walk out 40 centimeters from 10 to 50, and then they walk back 20, so 40 and another 20 gives me 60 centimeters. Well, let's try our equation and see what we get for the displacement. So the final is 30 centimeters minus the initial, which is 10 centimeters, gives me a grand total of positive 20 centimeters. Now, for positives and negatives, typically what we're going to do is we will typically take the regular directions, whether this is north, east, south, and west, or this is up, down, left, and right. And we're going to call these two our positives, just like your math class. And we're going to call these two the negative directions. Okay. Just to keep it simple, you don't have to. You could call down positive if you wanted to in a situation. You just have to be aware of that. So when you write your final answer, when I get negative 30 centimeters, I might translate that to say the bug walked 30 centimeters left. All right, so there's that one.